consider the circuit. You have one voltage source, one resistor, and an open circuit. Okay, and the value of this voltage source, it's a DC source, is V in times U of t. What's U of t? U of t is a function that is 0 before 0 and it's 1 after 0. That's it. Okay. This is 1. So it means the voltage source is connected to that resistor at t is 0. That's it. Okay. So let me define a current on the resistor I. This is input voltage. Let me define a voltage at this point. Let me say VC. Okay, so the input, the shape of the input voltage is like that. Before 0, it's 0, and after 0, it's V in. Its value is V in. Okay, this is in terms of volts. This is time. Consider these circuits. Question: what's the shape of the VC? Okay, this is time. Can you help me? What's the shape of VC? What's the voltage of VC? From minus infinity to plus infinity. Before 0, before t is 0, V in is 0. So what's VC? It's very obvious. Okay, obviously it's 0. Okay. What's the value of VC after t is 0? We expect VC is equal to V in. Why? Because the voltage of the resistor is I times R, and because there is an open circuit, what's the current of the resistor? 0 amp. So VR is 0. So it's very obvious that we expect VC to be equal V in. Okay, so my expectation is this. It's equal to V in. Okay, that's my expectation. Is it correct in real life? No. Approximately yes. Okay, in many times that's correct. But look at the circuit. Use a very long cable. Very long cable. Okay, instead of short cables, that's the circuit model. In real life, voltage source will be a, for example, battery. Okay, and a resistor is something like that. This is V in. This is VC. Okay. Instead, I connect a long cable. Okay, a very long cable. Or actually, let me do like that. I connect like that a cable which are very closer. Okay, that's important. I use a cable. It has two parts. Okay, two terminals, and I read VC from here. Question. Do cables dissipate some voltage? Assume resistance of the cable is 0. Okay, read the voltage here. What's your expectation now? What do you expect as VC? I expect same shape because cables have no resistance. There will be no voltage drop. Okay, I expect. So far we have learned voltage drop is equal to I times R. If R is 0, okay, if R is 0, so I should say V cable is 0. So I expect, okay, this is my expectation, expect VC is equal to V in. But when I measure, okay, when I observe the voltage at VC using an oscilloscope, using a device that draws the shape of the voltage with respect to time, this is my expectation. I expect this shape, or let me, okay, I have applied some voltage V in, and I expect VC like that. This is VC. Okay, this is my expectation. Expected. But in real life, what I see is this. Okay, before 0, no problem. I see what I have expected, no problem. But after the voltage change, I see something like that. Okay, so this is the reality. Okay, if I use a long cable, okay, and two terminals of the cable is very closer, like that, okay, you will see a delay at the output voltage. What's the reason of this? What's the reason? The reason is the capacitance property of the cable. Okay, there is a property called capacitance. Okay, what does it do? It's the capability of storing voltage. Okay. If there is a capacitance, if there is a component having capacitance property that stores some voltage, actually the stored particles are charged, okay, as charges. Okay, voltage is stored as charges. If you use a long cable like that, there are lots of charges on that cable, and to create some voltage difference on that cable, you need to move some charges. Okay, and you cannot move those charges instantly, so there will be a delay at the output, at the VC voltage. So if in the circuit there is a capacitance of some point, there is a capacitance associated with some point, you cannot change the voltage of that point instantly. Okay, capacitance, capability of storing voltage as charges. Okay, avoids instant change in voltage of point. So sometimes the capacitance property is a problem for us, okay, especially in let me say disadvantage. The capacitance increases with the frequency of the signal. Okay, avoids capacitance, avoid C is the abbreviation of capacitance, avoids very high speeds. Okay, that's a problem. For example, especially in digital electronics. For example, what's the speed of your microprocessor of your computer? What's the speed? How many megahertz? How many gigahertz? 2 gigahertz. Why isn't it very high, more than 2? Okay, why isn't it 4, for example? You can work your microprocessor at most. This is the maximum speed. Why the maximum speed is not 4 gigahertz or 10 gigahertz of your microprocessor? The reason, okay, 2 gigahertz, not higher than this, because of capacitance. Okay, because of the capacitance of the transistors in your microprocessor. Okay, sometimes it's a disadvantage, but advantage, we use the capacitance property purposely in many applications. We design special devices whose capacitance property is very high. Okay, I will explain later. That's called the capacitor. Okay, in delay circuits, we use purposely. Okay, if you want some delay after some action, you can use capacitors. And you can use in filters. You will see in later courses. Okay, capacitor has a filtering property. It filters some voltage. You design a capacitor circuit that filters the unwanted voltages, for example. Okay, for example, in radios, okay, you change the frequency, you hear some channel, you don't hear the others. How? There is a capacitor that filters the other channels. Okay, so in many applications, we use who are we? E. We use capacitance purposely. Okay, so we design special electronic circuit components whose capacitance property is dominant, high, and other properties, other electrical properties are negligible. What does it mean? We design a component whose capacitance is very high, but whose resistance is very low, inductance is very low. Okay, other electrical properties are very low, and we call them, okay, we call them as capacitors. So capacitor is a circuit component like resistor and inductor. Let's use a symbol for the capacitor. Let this be the symbol of the capacitor. It's a two-terminal device, A and B. There is a capacitor property of this cable. Okay, instead of that cable, I will use a capacitor to model this circuit. Okay, this is the real circuit. Let me model using circuit components. This was the old circuit model. And this is the capacitance property of the cable. Okay, so again there is a voltage on that cable, or the capacitance property, and there is a voltage, as you see. Let this be point A, point B. So there is a capacitor, there is a voltage we see. Okay, so let's try to find what's the shape of the voltage on the capacitor. Look at the voltages. This is the voltage of the source. Copy. This is the voltage of source. This is the voltage of the capacitor. Voltage, let me say VC. This is V in. So question, what's the voltage of the resistor? VR. To draw that voltage, let me apply a KVL. Start from this point. Can you help me? Plus V in minus VR minus VC. I have returned the same points. I have drawn a loop like that. Return the same point, 0. So, what's VR? VR is V in minus VC. Okay. Let's try to draw this shape. Okay. Here, 0 minus 0. Let me draw this value like that, and this is the value of V in. Okay, 0 minus 0. What's the voltage of VR before time is 0? 0. Good. What's the voltage of resistor at t is 0? V in minus, this is V in minus VC, 0. Value is V in. What's the voltage at t goes to infinity? At t goes to infinity, voltage of the source is V in, value is V in. Voltage of the capacitor is V in. V in minus V in minus V in is what? 0. Good. So it will be starting from V in and goes to 0. Because this shape is exponential, as you see, okay, this value minus this value I have to draw. So it will be something like that. At t, when t goes to infinity, when t approaches to infinity, voltage of the resistor should be what? Should be 0. Okay, good. Then, can you help me? What's the shape of the current? Okay, what's the shape of this current? As you see, the current of resistor is equal to the current of the capacitor. So there may be some current on the capacitor. Can you help me? This is the voltage of a resistor. Okay, a resistor. It has some voltage. It should be some current. What's the current of the resistor? Voltage divided by resistance. So if voltage is 0, current is what? If voltage is 0, current should be 0, of course. If voltage is V in, current is V in divided by R. So value of the current is V in divided by R. Here. Voltage of resistor is 0 as t goes to infinity. So current should be 0 as t goes to infinity. So the shape of the voltage should be the same of the shape of the current. Okay, because there is a linear relationship. So the shape of the current should be the same, like that. And that's consider this, the current of the resistor is at the same time current of the capacitor. Okay, IC is equal to IR, and also it's equal to I voltage source. Okay, so there is a capacitance, there is a voltage on the capacitance, there is a current on the capacitance. Okay, so consider this is the shape of the voltage of the capacitor, this is the shape of the current of the capacitor. Okay, so there is a relationship between the voltage and current, and that relationship is this. This is the capacitor voltage, current, the current of the capacitor is value of the capacitance and the derivative of the voltage. Okay, as you see, when the voltage is 0, current is 0. When the voltage is some value but there is no slope, current is against 0. When the slope is high, current is high. As slope decreases, current decreases. Okay, so current of the capacitor is dependent on the slope of the voltage. So derivative gives the slope. Okay, and actually you have seen this in physics 2 course, but let me remind, to make a high value capacitor we use two parallel plates. Okay, the actual shape I'm trying to draw in 3 dimensions. Okay, two parallel plates okay, this is the actual shape of a capacitor, two parallel plates. There is an amount of area. Okay, area, and there is a distance between the plates I will call as D, and we put some dielectric, some insulators between the capacitor plates in reality. Okay, in practice there is a dielectric between the plates, and there is a value called epsilon, the electric constant of the material between plates, and the value of the capacitance is epsilon times the area divided by the distance between the plates. Okay, so real capacitors that we use in the circuits are composed of two parallel plates. Okay, and there is a dielectric between the plates. So if you use this shape, the capacitance is very high.